Hello, my name is Yana Rios.
And I'm Amanda Diaz.
And we're going to be presenting about picture proofs. Pictures can be confusing to a reader when trying to understand a concept. Even though the majority of the times pictures tend to help in a problem, they can also lead to false results.
As the saying goes, a picture is worth 1,000 words. In any subjects, pictures can help someone understand the concept of a problem. Especially in math, pictures help students better understand what is trying to be explained by words. But if a picture is misleading, the whole concept of learning the right way will be wrong and eventually lead to getting false results for the whole problem. Therefore, we will determine if picture proofs alone are enough to understand the concept of a problem. Here we have a right triangle with one angle being 90 degrees. To find the third side, which is the hypotenuse, the side across from the right angle, we need a squared plus b squared to get c squared. You add those two sides together and then take the square root to find the length of the third side.
The Pythagorean theorem went through many different names and diagrams before resulting in the one we all use today. It was named for the Greek mathematician and philosopher Pythagoras. He founded the Pythagorean School of Mathematics in Cortona, a Greek seaport in southern Italy. Although he is credited with the theorem, it is likely that the Babylonians knew the result for certain specific triangles at least a millennium earlier than him.
The Pythagorean theorem. In a right triangle, the lengths of the sides of a triangle satisfied a squared plus b squared equals c squared, where c denotes the length of the hypotenuse and a and b denote the lengths of the other two sides. Direct proof, a way of showing the truth or falsehood by a straightforward combination of established facts without making any further assumptions. Proof by contradiction, an indirect proof established by assuming that the opposite proposition is true, that the assumption leads to a contradiction. Proof by cases, a proof where the statement is split into cases and each case is checked to see if the proposition holds. Summation. In math, summation is denoted with a large capital Greek sigma symbol, is the addition of a sequence of numbers. The result is their summation or total. An integral is a mathematical object that can be interpreted as an area or a generalization of an area. For our project, we're only going to be using one trig function, which is 1 over 1 plus x squared equals the inverse of 10.
The Pythagorean theorem states that a squared plus b squared equals c squared. Starting off, we have two squares with sides AB and one side C, C being slightly smaller than the one with AB. Square C is going to have an area of C squared. Now, having square C inside of the big square, we form four right triangles with sides AB. The area for the triangles will be AB, A times B over 2. Since we have 4, the total area of those 4 will be 4AB over 2, simplified being equal to 2AB. Therefore, the big square being A will have an area of C squared, which is the square C, plus the 2AB, which are the 4 right triangles. Now, with these facts, we can come up with the whole area, which is C squared plus 2AB. To prove it is true, square A has an area of A plus B squared. And this equals C squared plus 2AB. If we expand this, we're going to get A squared plus 2AB plus B squared equal C squared plus 2AB. Then we're going to solve for this, canceling 2AB from both sides, and this will equal A squared plus B squared equals C squared, which is exactly the same as the Pythagorean theorem. Now, if we are given numbers for sides A and B, if we let A equals 3 and B equals 4, we can find side C. For example, C squared is going to equal A squared plus B squared, which is 3 squared plus 4 squared. We evaluate the exponents, we're going to have 9 plus 16 equals C squared. Once we add them, C squared is going to equal 25, and to find side C, we're going to cancel the square root by getting the square root of 25, and this will equal C equal to 5. Therefore, we have sides A equal to 3, side B equal to 4, and side C equal to 5.
For our next proof, we start with two squares. One of side length A, the area of this square will be A squared, and a smaller square with side length B, which will be B squared. When we remove the segment attaching them and construct two right triangles, these will have A, B, and a hypotenuse of C. Now we get the right triangles created that we have here. We rotate the right one clockwise and the left counterclockwise to meet at the top of their vertex. Then we try to meet them at their bottom vertex, as we have here, and we try connecting them. Notice they form the same rounded shape in both pictures when you try to connect them. Now, going back to the first shape, we will get these two right triangles and try to finish off square C. And we will get a perfect square with these right triangles. And as you can see, this square fits into this triangle perfectly and completes it to make one triangle square.
Moving on to our third proof. We have the summation from 1 to infinity of 1 over 2 to the k equal to 1. Given k equal to 1, we're going to have 1 over 2, which is this part of the square. Then continuing, we're going to have 1 over 2 plus 1 over 2 squared, which is 1 over 4, which will be almost 3/4 of the square. Continuing, plugging in 3, it's 1 half plus 1 over 4 plus 1 over 2 to the third, which equals 1 to the 8th, which will be now almost completing the square. Continuing with k equal to 4, we're going to have 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 2 to the fourth, with equals 1 over 16, which will now be this whole thing. As we continue, we're going to see that the pieces get smaller and smaller to almost completing the whole square. As we try to get to infinity, the whole square will be almost completed, equaling the fractions to 1. Here we have the integral from 0 to 1 of 1 over 1 plus x squared should equal pi over 4. Once we evaluate it, we're going to get the inverse of tan. Evaluating the inverse of tan from 0 to 1, we're going to get inverse of tan 1 minus inverse of tan 0. The inverse of tan to the 1 equals pi over 4, and the inverse of tan to the 0 equals 0. Therefore, the whole problem just equals to pi over 0.
As you can see, sometimes pictures can help us understand a concept, as in the summation problem. It can also be difficult relying on a picture alone for a proof, as we see in our other problems. These are the references we used for our project.
And thank you for watching our presentation.